Okay, welcome everyone to episode 49 in our space shooter DevVenture. So we were busy with the flee and arrival behaviors in our last session, and we were trying to figure out how we are going to implement flee, right? Because until we have flee, we can't really do the full pattern, and we kind of have to do the full pattern, right? And as we found out, arrival is a critical element that we do actually need in our seek behavior. Because once we reach a critical threshold that we will define at some point, the arrival threshold, then we need to slow down the enemy AI. Well, the AI actor, whatever it is, right? If it's a mining bot or a pirate ship or a defender, if you're playing as a pirate ship, then you want the AI to slow down once it reaches that threshold, the arrival threshold, right? And then some other behavior should take place, right? So once it reaches the arrival threshold, it should slow down and start shooting if it's a pirate or a defender, right? And then once it reaches the flee threshold, it should swerve and actually flee away, like move away from the target until it breaks out of the flee threshold and the arrival threshold and even a seek threshold. And then swoops back again, right? And we can define those three thresholds. We can have three values, right? So there's a critical radius, a collision avoidance radius, and then there's a firing range radius, and then there's a chase range, right? So a pursuit range. So once something is within the pursuing range, it starts seeking the object, and then once it's within arrival, or what we call shoot, once it's in shot range, I don't want to say shooting range or firing range because it kind of sounds like the firing range scene that we had set up before. So I'll say shot range instead, right? So once it's within shot range, it can then actually shoot and have a better chance of hitting the target, right? The bullets are flying fast enough, or the projectiles are flying fast enough to cover the gap and actually collide with the target, and so on. So let's just carry on. We'll go down to where we left off last time, which was here by arrival. So once it reaches the slowing area, or what we'll call the arrival region, right? The arrival radius, then we need it to start reducing its speed. If it's a stationary object, it can come to a standstill and start firing, right? If it's a moving object, it just needs to slow down enough to pursue without losing any distance, right? And without increasing the distance too much either. I mean, decreasing the distance too much either. So without catching up too much, because if your target is moving like this, well, like that, right? You don't want to be moving with them or faster than them, that you then have to start swerving away again, right? You kind of want to keep that same distance the whole time, so you get to within optimal shot range. So not too far back that you're like just in shot range and you're less precise, and you don't want to get too close that your enemy can fire back, or that you are about to have to start doing flee maneuvers, right? Because if you're too close, you don't know what the target is going to do next, right? Maybe they start slowing down even more, and at that point you kind of have to flee, because now you're too close again. Now you have to flee, right? So you want it to be somewhere in the middle. And yeah, so let's just go over the stuff. I don't want to talk too much about it. We'll just cover all the details because there's quite a lot still, as you can see from the scroller. And it is quite dense, right? Because we have to go through code and try and understand everything that that is being explained. So yeah, anyway. So when the character enters the slowing area, its velocity is ramped down linearly to 0. This is achieved by adding a new steering force, the so-called arrival force, and the steering force is then added to the character's velocity vector. The result of this addition will eventually become 0, meaning that nothing will be added to the character's position every frame. So there will be no movement, right? So the a new steering force is added to the velocity vector. Oh, I get it. So a steering force can be positive or negative, and if you're adding it and you're adding a negative force, you're subtracting from the velocity, right? So if your steering force is pulling backwards like brakes, then your velocity will decrease towards 0, and once it gets to 0, then the steering force becomes 0 as well, and then 0 plus 0 is 0, right? So there you go. So velocity is the truncated addition of velocity plus the steering force, truncated according to the max speed. I think we covered this. And then position is just the addition of velocity to position. And then the function definition of truncate. So in order to ensure that the character will gradually slow down before it stops, the velocity should not become 0 immediately. The gradual slowdown process is calculated based on the radius of the slowing area and the distance between the character and the target. The radius of the slowing area and the distance between the character and the target. Excuse me, I'm trying my best not to yawn. Desired velocity is target minus position, right? The distance from the target to the position is just the difference between them. And then, well, no, actually that's the velocity, never mind. Then the distance to that is the length of desired velocity. So doing this, because target and position are both vectors, your resultant is a vector. And so you want the magnitude of this vector to get the actual distance. Because remember, distance is a scalar value. Distance is a scalar value, right? If you wanted, the desired velocity is actually a displacement vector. Because you're taking two positions. You're subtracting those two positions. And you're getting a vector. And the vector equivalent of distance is displacement. Because it's got the direction and the actual space coverage. So yeah, so now we scalar convert that. We say we get the length of the desired velocity. Then we check the distance to detect whether the character is inside the slowing area. So if the distance is less than the slowing radius, then the desired velocity is the normalized desired velocity. So we get the direction, right? Times the maximum velocity. So we get the maximum radius times the fraction of the distance over the slowing radius. So we then bring it down within the range. So, and then once and then if it's not, so then that's the if statement. Then there's an else statement. So if it's not less than the slowing radius, then the desired velocity is the direction of the desired velocity times max velocity. So full speed in whatever direction. And then set the steering based on this, right? So steering is the desired velocity minus velocity, which is current velocity, right? And if the distance is greater than the slowing radius, it means the character is far away from the target and its velocity should remain at maximum, like we said, right? So that's what we saw here. If the distance is less than the slowing radius, so for example, once it's within the slowing radius in the slow region or the arrival arrival radius, then it means the character has entered the slowing area and its velocity should be ramped down. The term distance over slowing radius will vary from 1 when the distance equals slowing radius to 0 when the distance is almost 0, right? So a percentage. It's a percentage of the distance from the exact location of the target to the slowing radius full distance. And then this linear variation will make the velocity smoothly slow down, right? So this would be the equivalent of doing some kind of linear interpolation, so like lerp in Godot engine. But the point is, this is supposed to be independent of any environments, right? So independent of game engine, independent of any physics simulation software or whatever, any web-based graphics program, anything like that. So yeah. And then, as previously described, the character movement is performed as follows. Steering is desired velocity minus velocity. Velocity is the truncated velocity plus steering, truncated to max speed. And then position is just position plus velocity. If the desired velocity is ramped down to 0, then the steering force becomes negative velocity as a consequence, and that steering force is added to the velocity. It will result in 0, making the character stop moving. Like I said, right? So once you enter the slowing radius, then your steering velocity becomes negative and it starts chipping away at your velocity until velocity gets to 0. And then you're adding 0 to 0, in which case you don't go anyway, right? Below is a demo showing the arrival behavior. It doesn't work because it's not there. What the arrival behavior does really is calculate a force that will be equal to negative velocity, thereby preventing the character from moving as long as that force is in place. The character's original velocity vector does not change, and it continues to work, but it is nulled by the steering addition. Nulled as in made 0, not nulled as in made invalid or undefined. So if the arrival steering force is lifted, the character will start moving again using its original velocity vector. Right? So you set the target to something else. Now this arrival region is gone because it's no longer the target, and the arrival region is shifted to whatever the new target is. And now again the check goes, oh, but our distance to the target is greater than the arrival radius. Therefore, we can go back to full, to maximum speed in the direction of the target. So let's do that. And then it obviously adjusts the vectors and such so that it does an interpolated curve towards the target, and also ramping up towards maximum speed. And in conclusion, the flee behavior makes the character move away from the desired target, while the arrival behavior makes it slow down and stop at the target's position. Both can be used to create smooth escape or follow movement patterns, for instance, but they can also be combined to create even more complex movements. This tutorial described more about steering behaviors, explaining the flee and the arrival behaviors, and over the next few posts, we will learn more about behaviors. So keep up to date by following us on the social media handles, right? So the point is, arrival can be useful in more than just what we want, right? So for example, if you're thinking of having your vessel park in a hangar, right, and take a specific spot in the hangar bay, you can use arrival for that, right? And it doesn't have to be an animation. It could be an animation. An animation would be simpler, right? Where you literally just use keyframes. So you stop all movement, you stop all controls from script, and then you just play an animation that moves the ship physically through space, and it does a nice, neat and preset curve and follows and slows down and lands and does all the beautiful things, and it shoots like jets and whatever and stabilizes itself and lands and shuts down all the stuff and plays the sound effects and particle effects and everything, and it looks amazing and blah blah blah, and then it's done, then it's landed. And now if you want to, if we want to have that feature, we can then let the player get out of this vessel and start running around the hangar bay or start running around the capital ship or whatever. Maybe we want that. I definitely think that would be an interesting element to add to the game later, but not now. For now, we'll just do the basics, right? And then we could add it if we build a single player campaign. We could add it that the player can get out of their vessel and not only explore the capital ship, but also start looking at how to improve it or upgrade it or expand it or whatever, right? Maybe they want to switch vessels, and the best way to do that, of course, is to park the vessel in the hangar and then jump into the next one, and then the game mode switches, right? Or something, whatever, right? But the point is, if you want to park your vessel, you've got two ways to do that. You can do it by animation, which I just described, or you could use arrival. So once the player reaches a certain radius, and they go through some kind of collision barrier or whatever, and you make it really deliberate, so they have to deliberately go there in order to initiate this like arrival sequence, the parking sequence, rather than just a general distance to the hangar bay, right? Then you initiate this arrival behavior, and it will then do what it's supposed to, right? So it will slow the player down towards the parking bay and land. Of course, this is a much more programmatic way of doing things. It's not going to be as fancy. It won't have all the twists and turns and the animations, like adjusting all the flaps and stuff as it's like stabilizing and pushing out different thrusts through all the the jets and puffing down on the landing bay, and then the smoke emanates from below, however you want to do the landing sequence, right? And then all the engines are like ramping down and you can hear it all, and because you're in the hangar, it's not space, so you can actually hear the engines like and the thrusters and all that kind of cool stuff. So you could do a combination of the two, but the point is, like, if you want arrival for the AI, for the AI actors, you can do that, especially when you're talking about minor vessels going to deposit their cargo or offload their cargo at the drop-off points or the collection points, however you want to phrase it, right? You could do arrival there. But I think what's even more interesting for that stage would be queuing, because you want them to queue, right? If you've got multiple mining vessels and they've all gathered their resources and they all want to go and drop off their resources at the capital ship at the same time, they can't. They have to queue, right? And so you're going to have to set up this queue, and you can make the game in such a way that this queue is secured, so the pirates can't get them once they reach the queue, right? Because it's got massive turret guns or whatever that are guarding this queue in the depot. So the pirates are supposed to attack the mining vessels before they reach the safe zone, right? And then once they are in the safe zone, then it's already too late. They can't get. They would be stupid to approach because they would just be shot down, right? And these guns don't mess around. They're not like defenders that are, flying around and orbiting and turning and steering and aiming and all that. They are stationary cannons that can calculate very precisely. And they are I would say aircraft, but it's not aircraft, it's spacecraft, right? They are anti-spacecraft weapons designed specifically to do area of effect blasts, right? So it doesn't just shoot a plasma bolt at a very precise location to, hit and damage a target. It's like fly and boom. Like almost like missiles, but not quite missiles. And yeah, high damage, high output, high fire rate, high precision. Basically guaranteed defeat for any pirate that comes close, right, within the shot range of this gun. So the pirates actively avoid that zone. So it's basically infinite. There's if you're talking about a cost per location or per region, when you're talking about pathfinding, we'll get to pathfinding maybe in another kind of DevVenture series where I deal with nav meshes and terrain and actual pathfinding, right? But then again, this is kind of pathfinding, right? It's just volumetric pathfinding as opposed to surface level pathfinding. So when it comes to pathfinding, you've got this idea of graphs and the cost for transition from one node to another over an edge. So an edge has a cost between the nodes in the graph, right? Now, you could consider the safe zone to have an infinite cost, right? So there's no way that a pirate can go over this edge to that node. It's too costly. So yeah, okay. That was a digression, and I'll try my best not to digress too much. But I did think that was an interesting anecdote. Yeah. So we finished all of this, and now we can get back to the game engine, right? And now we can actually go through all of this and do the flee and arrival behaviors, right? So now we've got two other behaviors. And what I want to do is bring in the arrival logic onto seek, right? So ideally you'd want them to be separate, right? So you've got excuse me, I didn't mean to hit the microphone like that. If you've got a situation where you don't want your AI actor to arrive and you only want them to seek, then of course you want them decoupled, right? So I think we will probably have to make an arrival behavior node, right? And we'll have to make a flee behavior node. So let's work on flee first, because again, like I said, we've got the seek, shoot, flee pattern, and we might need to add in arrival. So seek, arrive, shoot, flee, and then seek, arrive, shoot, flee, seek, arrive, shoot, flee. I never thought about arrival until we actually learned about it now. So that's why I never mentioned it as part of the pattern. It's not because I was deliberately withholding it or anything. It's just something I never considered. Okay? So, yeah. Now I want to go into Godot engine. So let's do that. And here we have, so that's level manager. I want to do behavior seek. Type behavior seek. Okay. Now I want to create a new script and a new node. Right? If I go into the scenes over here, and I can go into behavior components, steering behaviors, we've got seek, and now we need arrive. Why is shoot not present here though? Player components, NPC components, general components, steering and general behaviors. Oh, I see. Because shoot is a general behavior, apparently, as opposed to a steering behavior, which is seek, right? Okay, so let's add in here a new scene, and we'll name this, it's a ordinary node. We're going to call the scene, so seek is uppercase seek. So let's do uppercase arrival. Okay, and we'll say okay. And now attach from arrival, we'll attach a script here. We'll call this behavior arrival.gd underscore arrival.gd. Okay, and we will save this in steering behaviors, behavior components. No. We'll save it into scripts, behaviors, student behaviors, behavior arrival.gd. Okay, so we'll save it there, and off it goes. Create that, and now we have it, right? And now we can actually say class name and then extends, right? So no, extends and then class name. So at the bottom here we can say class name type behavior arrival, and save that. Type behavior seek, type behavior arrival, and now I want to take the code. Wait, I just want to check something. What is this thread actually called? Combat logic and the core combat system implementation. Didn't I have one for the playable scene? Okay, I've got that one. I suppose it does account for part of the combat system. Anyway, what I need to do now is get that Envato tutorial and paste it in here on Perplexity and get its opinion on how to do arrival in Godot Engine, knowing what seek is, knowing how all of the stuff work together, and so on, right? Again, we can discuss with Perplexity how exactly we want to do it, right? We don't have to let Perplexity do all the heavy lifting, and I don't want it to. I want to be the one to think about the stuff myself, and then just have Perplexity do the heavy lifting stuff, right? So the like the so-called grunt work of writing out the code, and we'll do the review of the code and edit the code and so on. Okay, so where is this tutorial? Here. So I'm going to copy all of the arrival and flee arrival stuff, right? So let's just copy the just excuse me 1 second. Someone is trying to call me. I just have to send them a quick message to tell them I'm not available. Okay. So as I was saying, I need to copy the tutorial and then get the algorithm from Perplexity. All right, so let's do that. We'll just copy everything. Actually, I'm just going to copy the link and paste it in Perplexity. That's fine. Let's do that. So here is a tutorial I'm following about flee and arrival behaviors. Please help me create the arrival behavior first, and then we can do flee after that. Here is what I have in mind. So I need to now explain what I have in mind to the AI, right, to Perplexity. So here's what I have in mind. the AI actor comes within the so-called arrival radius and signals that it has done this. Then the pattern should be updated to include the arrival behavior for the attack pattern. We want to bring the AI actor to a so-called sweet spot within the shot range, so there is increased precision with minimal risk of return fire. If any. Going right up to the target is risky, as the flea I'm writing on and on the same bullet point. Okay, so for attack pattern, we want to bring the AI actor to a sweet spot within the shot range, so there's increased precision with minimal risk of return fire. And then another point, we should add logic to detect if the target is missing. If the target is moving, and if it is, then keep a constant following distance to the target to reduce the chances of needing to flee, while increasing the time for firing at the target, right? And then if not moving, make arrival stop the AI actor at the sweet spot. So firing can continue uninterrupted until the target is destroyed. Right? So let me just go through this one more time. The AI actor comes within the arrival radius and signals that it has done this. Then the attack pattern should be updated to include the arrival behavior. For the attack pattern, we want to bring the AI actor to a so-called sweet spot within the shot range, so there is increased precision with minimal risk of return fire, if any. And then we should add logic to detect if the target is moving, and if it is, keep a constant following distance to the target to reduce the chances of needing to flee while increasing the time for firing at the target. And if not moving, make arrival stop the AI actor at the sweet spot so firing can continue uninterrupted until the target is destroyed. Okay, so I'm just trying to think of everything else. Okay, yeah, one more thing about flee. If the target is a moving hostile enemy, then the flee behavior kicks in once the enemy comes within the flee radius. Since the need to swerve out of the way is not or rather is dependent on the AI actor's enemy movements, the flee behavior is less important, or rather not less important, but is less likely to be invoked than the arrival and shoot behaviors. What do you think of this adjustment? Okay, so your adjustment makes sense and fits well with steering behavior theory. Arrival refines seek, so the ship reaches and maintains a so-called sweet spot, while flee handles close-range danger. For your 3D AI ships, add an arrival radius, or the slowing zone, and a sweet spot distance, the ideal firing distance inside that radius. And then behavior seek currently accelerates to top speed and stops abruptly within 2 units. And then arrival behavior seek currently accelerates to top speed and then it stops abruptly when within 2 units, 2 units of distance from the target. Whereas arrival should move like seek when far and then gradually reduce speed once inside the arrival radius, aiming to stop at the sweet spot distance from the target. On entering or maintaining the sweet spot, emit a behavior completed or arrival or completed, whatever signal, so that the tactical layer can transition to shoot. And then stationary versus moving targets. A stationary target we slow down and stop at the sweet spot, and we just keep facing the target and let shoot handle continuous firing, right? So you just stop, you park, you take your aim, and you just keep gunning until there's no more target, and then off you go, right? So that's the stationary target. And then for a moving target, we have threat arrival. We just threat arrival is something like excuse me, not threat. I misread that. We treat arrival as dynamic following. Okay? And we continuously recompute the desired position as the target position minus direction times the sweet spot distance. We steer to that point with arrival logic, so you maintain roughly constant distance. And this reduces the need to flee, because you are not closing too much, and you can keep firing longer, right? Except if the enemy is closing the distance to you and forcing you to flee, right? So that could be a valid strategy of the player. If the pirates are like harassing you, you can just chase them and get them to swerve. And when they swerve, then you can kind of fire at them. So there's all kinds of things we can think of, right? And of course, you don't want it to be too simple that their behaviors can be learned and, in quotes, solved. You know, that it's like, oh, I'll just deal with the pirates with this particular play. You know, like in a playbook or whatever, you have a play. Oh, we'll just do play 45 on this in this scenario or whatever. I mean, it would be nice if we could force the player to come up with 45 different plays. That would be really interesting. But yeah, realistically speaking, it's probably just going to be like 5 or 6 plays. Hopefully more. I don't want the AI to be like, oh, it's just 1 or 2 plays. That's really going to be too simple. Anyway. Detecting motion can be simple. Right? Store the last target position, and if the distance to the last target position is greater than a small threshold over time, consider the target moving, and use follow mode, otherwise treat it as stationary, right? And so this small threshold is literally just noise, right? So there's always this noise margin whenever you're doing any kind of measurement. You should include some kind of error margin, right? And that's just to cover any kind of noise. So if, for example, the target position you're aiming for is not the exact origin of the object, and the object happens to be rotating in place, for example, then that noise margin should be big enough that this rotating in place doesn't count as moving, because if it does, it's going to mess with everything, right? The only time it should count as moving is if it's a huge rotating in place, right? Like it's some kind of container at the end of a large arm on the capital ship or whatever, and that's being spun around the whole capital ship's like size. And your objective as a pirate ship is to destroy this canister. In which case, yes, you will have to add the following behavior in that case, because the arm is doing this like arc, and as it does, you have to chase after it. So there's that to consider too, if you want to. But if you do your rule sets generally enough, right, you make them as general as you can, then all of these cases will be dealt with at least 90% of the way. And then if there's any special edge case, you can just deal with those specifically, right? Or you can refine your rule sets to accommodate them. Now, how it fits into your current pattern, right? So you can extend your pattern dictionary. For example, attack now has arrival, shoot, and flee, right? And then you add a new behavior, arrival.gd, similar structure to behavior seek, which activates enemy ship ID. It's got activate with enemy ship ID and parameters. It's got a process function taking in delta with arrival logic and motion. Then it's got behavior completed, the signal, .emit, enemy ship ID, arrival, completed, data, when the sweet spot is reached and stable. And then in the tactical layer, the NPC behavior manager already knows how to chain behaviors. Adding arrival as another behavior key is just to add a child node called behavior arrival in the behavior nodes group, and then ensure that its class name and name map and that its class name and the name map to arrival, to the arrival key, like your seek and shoot do, and then the flee hook for later. Add a flee radius. If a hostile target comes within this radius, the flee behavior will activate, example via the pattern or a tactical override. And because arrival keeps you at a safe sweet spot, flee should trigger less often as you intended. And if you'd like, the next step can be sketching the concrete GD script for behavior arrival based on your existing behavior seek with arrival radius, sweet spot distance, and moving target versus stationary target logic. And yes, exactly, that's what I want to do. I want to do the arrival behavior first and then focus on flee afterwards, because flee, like I mentioned, while it is important and it's an advanced behavior that we do need to add in, it's critically important for the cases where it's needed, but it's less likely to happen, and so it has a smaller priority than the one that's more likely to happen, even though it might not be as advanced, you know. So yeah, let's do that. I'm going to give it the code I have so far, which is literally just this. So here is the code I have so far on behavior arrival.gd. Let's get to work implementing this algorithm for the game. And there we go. You can implement arrival as a refinement of your existing seek with extra parameters for arrival radius and sweet spot, plus simple moving target detection. Okay, so extends node, class name, type behavior arrival. We have a signal for the behavior completed. Of course, when the signal is, when the behavior is done, we need to have that signal. And we'll probably have to connect that behavior completed to the enemy ship controller. Although, remember, the signal behavior completed should be the same for every behavior by definition, so that the enemy ship controller doesn't have to have multiple functions attached that you know, I'm actually torn between the two, right? Should it have a singular so-called master function to deal with all completed behaviors, or should it have modular functions, one function for each behavior that is completed? Because if it has a function for each, you can kind of see how that's more modular and you can do more specific things, but at the same time, it also opens up the door to a violation of the dry principle of don't repeat yourself, right? And in that case, we'd rather just have a master function that deals with everything, and then it's got like special cases and stuff inside it. I think the first option is better, the master function idea. So we'll go with that. Okay. Now we have basically the same thing as seek, like it mentioned, except now it has to slow down towards the sweet spot and emit signals and so on when it's ready. So signal behavior completed, enemy ship ID integer, behavior type string, status is a string, and then data is a dictionary. So we have the variable enemy ship of type enemy ship. The target node is a node 3D. The target position is a vector 3D. Parameters is a dictionary. Is active is a boolean and set to false automatically, because we don't want it to be active all the time. We just want it to be true when we activate it. And remember, there's an activate function we're going to call that sets is active to true. And then in the process function, we're checking if it's not active, return, otherwise do the stuff. So yeah, and you'll see that here somewhere. If not is active or not enemy ship, then return, right? So then I was right. I'm not necessarily claiming that you were wrong, just that I was right. So, so please don't be too upset about that. Okay, so yeah, we've got those variables. And then arrival tuning. So export a variable arrival radius, which is a float. We can set it to 40 by default. Doesn't have to be 40, but we can start it out as 40. Okay, and then that's the slowing down inside this distance. The start slowing down inside this distance. And then we have another exported variable called the sweet spot distance, which is a distance within that radius, the ideal distance from the target for firing. And then export the variable stop tolerance. Remember, like I mentioned, that's the noise threshold. If the position of our target differs beyond that over a certain interval of time, that means it has a speed or velocity and it's moving, and therefore we should treat it as a moving object. If not, it's not moving, and we should treat it as a noisy stationary object instead. So yeah, the stop tolerance, how close to the sweet spot, counts as arrived. Oh, okay, never mind. And then a variable, another exported variable, follow distance tolerance, the allowed deviation when following a moving target. So if the target is moving, our distance to the target can be, if we have the follow distance set to 20 and this margin is 3, that means we can have 21.5 or 18.5 up or down, plus or minus 1.5 within 3 distance units of the desired following distance. And that's fine. And then we've got motion detection. So this is where I was actually talking about the motion detection, right? So the last target position is this vector 3. The target is moving is set to false. Export variable moving threshold float 0.5. The distance change to consider as moving. So that's your noise threshold, right? And then we've got the activate function, sets the enemy ship as enemy ship. And if it's not an enemy ship, if we can't initialize the enemy ship, we push an error, we set the behavior completed signal and we emit it, and then we call return. Otherwise, parameters is behavior parameters, is active is true, we get the target node or position, and then if parameters has target node, then the target node is parameters target node, and then if it also has else if, or if it has target node path, then get the node path and set that to be enemy ship.get node parameters target node path, right? If the target node exists, then we set the target position to be its target position. Otherwise, if parameters has a target position specified, then we use that instead. Otherwise, we push an error saying there's no target specified, and we emit the completed behavior with failed. The reason is that there's no target, right? And we set is active to false and call return. That is straightforward, simple, clean, and pure, right? And the last target position is then the target position, and target is moving is set to false. We then print arrival behavior activated for ship, enemy ship ID, targeting, target position, right? And then we've got function deactivate, setting is active to false and calling a print message to say that we've deactivated it. Then we have a process function taking in delta, returning nothing. If is active is false or the enemy ship is null, we call return, right? And then if this check passes, we return. If it fails, i.e. it fails to find any reason to discontinue, in other words, the process function succeeds. The check fails, but the function succeeds. Then if the target node and is instance valid of target node, then we so if there is a target node, it's not null, and is instance valid, so it's an instance that is a valid target node, then we create a new target node position a new target position called target node or global position, and the moved distance is a new target position dot distance to. So we calculate the distance to it. And then if moved distance is greater than the movement threshold, so if it's moving more than just some noise, then the target is moving and we set that to true. And the last target position is a new target position. And then the target position itself is also a new target position. So we have current and previous positions, right? So if you think about it, it's like, I'm here, I was here, and now I'm here, I was here, and now I'm here, I was here, I'm here, I was here, like that. So that's what last target position versus target position is. It's the two differences, right? So where is the target now and where was it before, and what is that distance, and is that distance greater than noise? And so this is all just to detect if it's moving. If it's not null, I mean, if it is null, if target node is null, or if the instance is not valid, then we say that the target node is set to null. And then this is a fallback to a static target position if node is lost. And then if target is moving, then process arrival follow delta, else process arrival static delta. And so these are two functions, process arrival static, process arrival follow. And yeah, it's a huge amount of code. So unfortunately, we've basically run out of time. Just as things started getting interesting, we ran out of time. So I'm going to stop here, and I'm going to do my shout out to Cubes, our junior DevVenturer. Thank you so much for your support. It means a lot. And to everybody else, please do go and check coffee.com/mtkdev. You're welcome to support the channel in whatever way you can. And if you can't support the channel financially right at the moment, you don't have to be a member to support the channel. You can do a once-off donation. And if you can't right now, then at least give this video a like, subscribe to the channel, and share the link with as many people as you can, right? Because if you can't support the channel financially, maybe one of them can, right? And if you support the channel, you get to see more of this content. So yeah. And then also, please do go and join the community, the Discord community. There's a community on YouTube as well, if you want to join that. But the primary community is the one on Discord. The link is in the description of this video and all of the live streams I've done so far, right? It's the same link, and it's open to whoever has the link. You can join the community. So go ahead and join the community, and I hope to see you there. So thank you so much for your time and your attention, and I'll see you all in the next live stream.